Welcome to the radar system course. We continue discussion from this match filter receiver. So we have defined this RFF function earlier that RFF is equal to what? We say that it is about a function for what? Whatever the signal we have, okay, that is about a signal out function that is about a T by N here. Okay, in terms of what? A signal out. So that this one is about a square now. So that this particular function with respect to the output of a signal and a noise here. Now that output we can define in terms of a filter function, filter response function. So S of f, RFF is equal to what? S of f, H of f, this one function. That is about the output function. And noise is nothing but what? N0 by 2, 1, and is infinity to infinity, H of f. This one is about a portion of a noise. This one is called as a noise function. And this one is nothing but what? A output function. You can say that this one is about a output one. Okay, so now this one is about output. So S out, at R of F, we have to obtain that is about a ratio, and that ratio will define you what is the signal to noise ratio. So output function in terms of H of F and a noise in terms of a H of F at a receiver one. So now we need to use a Sheward inequality function. So P complex P dx is equal to Q complex Q Px greater than or equal to PQ dx. And P complex is equal to what? We say that S of f exponential of j twice by ft. Q is equal to h of f. So we can say that this one is about a Q. This one is about a, we can have S of f here. This and this one is nothing but a S of f. Okay. That is about a P now. And this one is about a Q now. Okay. So we can say that from this we have defined, okay, so we can say that P is equal to this one. Okay, so we can consider the expression of RFF in terms of H of F square TF and S of F square DFF. That is about a first function. Okay, and this one divided by noise in terms of a H of F here. Okay, and then equal to, we have the, that's about, this one is about a twice we have to write. Okay, so we can say that H of F function in terms of using this Sheward inequality function. So we can say that in terms of a signal now. So S of f here. Okay. So this one is about S of f square df by n0. So this one is cancel it. So we have only the n0. Okay. So this one is nothing but what, whatever the ratios we are expecting, that is a S out by n here. And similarly, we are getting this RL. F of f is nothing but a noise function, that sorry, signal out function f of f, and this one is about a noise. So we can rewrite here RFF that S of f is nothing but the energy. So we can consider that this particular portion we can rewrite S of f as a energy now. This one is about E now, and this particular portion is about a noise. So we can rewrite this expression, of a RFF is equal to what? Twice of E divided by Ng. Okay, so this one is about it. We have the RF. Generally, we can say that it will be less than or equal to RF is equal to less than or equal to twice of E by N0. And this, we can say that a frequency response function which will maximizes a peak signal to noise ratio, that is about a RF, and that will be obtained through what? A shared inequality. And we have defined the h of f function in terms of what? The gain as well as the exponential function. Okay, so earlier we have defined that a h of f is equal to k 1 into a s of f complex conjugate of f s here function and exponential of minus j twice by f t1. This a this we can say that it has a constant gain, and this we can say that a complex conjugate of the function. And generally, this particular function, this RF, is equal to whatever we are getting. That is about a whatever the signal, and that signal has some particular energy. So that ratio will be the maximum. In that case, we have that ratio twice of what? A maximum energy of the signal and there a noise power. Okay, so that noise power is about a n0. Okay, noise power per bandwidth, that's about a n0. And generally we define that noise power per heads of the bandwidth, that's about n0. And that n0 we can define in terms of what? A k, t0 and a f. Okay, or you can say that k is nothing but what? The Boltzmann constant. T0 is nothing but what? A standard temperature of a 290 K, and this F is nothing but the a noise figure. So noise bandwidth N0B. Okay, so KTB F. Okay, KTFB. Okay, so likewise. So this one is about a noise function, and that will define you. So what will be the ratio, maximum signal to noise ratio by this match filter function? Okay, so that is about a RF here. And then again, we can say that the output of a match filter function is not a replica of a signal. Okay, so already we say that the output of a match filter h of f with respect to the gain of this. Okay, so what we have defined earlier, that is a h of f is equal to what? A gain, then a complex conjugate of s of f exponential of minus j twice by f t1. So this one is nothing but a signal out. Again, that will be the constant term here. And we say that the output of this particular match filter function is in terms of a whatever the input signal to the receiver there. And then we need to increase the signal to noise ratio. So when we are increasing the signal to noise ratio, then we need to consider that whatever the bandwidth here. Earlier we say that for a wide band signal to noise ratio decrease, for a narrow bandwidth a signal to noise ratio improve, but the part of a signal we lose or part of the information we lose. So that's why we need to consider the optimum band. So the same condition is here. While detecting a signal, we in terms in a noise, so we need to preserve important information of a signal or a whatever the shape of the signal there. Okay, generally information. We need to get the important information of the signal rather than what we can say that whatever the signal to noise ratio maximum and all. Generally, we are expecting that a higher signal to noise ratio, but we need to find out the at same condition what will be the shape of a signal. If we are not getting the shape of a signal, we are not preserving the information. So then there is no role of the maximizing the signal to noise ratio. So in that case, we need to use the output of a match filter to preserve the particular shape there, and that output of that match filter may be correlated with a replica of a transmitted signal, except of this time delay t1. So that's why a cross correlation function, cross, you can say that correlation function is equal to r of t of a two signals, and that two signals are nothing but what we define. The two signals are phi of t and as of t. Okay, that is cross correlation function of a two signal y of t and a s of t, and that will be both the signals. Okay, two signals, they have the finite duration. So that's why we can say that a r of t is equal to minus infinity to plus infinity with respect to that what will be the output response of the function. Okay, so if we can define this particular two signal function instead of a t here, we will define of a lambda here. So y of lambda s of lambda minus t to understand what will be the timing and all information. And then output function y of t, okay, y0 of t, and that output function based on the what will be the filter response there, h of t, and that filter response we are getting from what, from what will be the input signal there. So that input signal we say that s of t plus n of t. Okay, okay, likewise y now. So from this we can find out a y0 of t minus infinity to plus infinity y in of lambda h of t minus lambda d lambda. Now the condition is that if the match filter, okay, we can say that whatever the filters we consider there, that will be supposed to be a match one. Okay, so we can say that instead of h of t, we can say that it is about a match filter. Then in that case, h of lambda is equal to what? S of t1 minus lambda. Then we rewrite the equation here, that is a y0 of t is equal to, we can say that a minus infinity to plus infinity y in of lambda here into f of t1 minus t plus lambda into t lambda is equal to what? A r of t minus t1. Okay, that is about a cross correlation function. Cross correlation function that will be obtained from the it received signal as well as the replica of the transmitted signal, and that received signal is to be corrupted by the noise. Okay, so we can say that whatever the two signals we have, cross correlation function to be defined with respect to the input signal as well as the replica of the transmitted signal. Only the condition for a particular duration of a time t1. Okay, that we are there. So we need to build a replica of the transmitted signal through the match filter via a frequency response function. So that's why we can say that a y in of t here we are getting, and that y in of t is nothing but what? That is defined in terms of what? A signal as well as a noise here, s of t. So we need to remove that or we need to increase the signal to noise ratio by preserving the signal function. So that's all about what we can say that the match filter and their function with respect to the a wide Gaussian noise. So then a filter we are using, and that filter efficiency is depending upon the what type of a signal we supposed to propagating here, or we can say that what type of pulse we have. Okay, input signal pulse, and based on that we can define the efficiency of a filter. Generally we can say that the efficiency is nothing but what, a peak signal to noise ratio. So if your filter is matched, so efficiency is higher, and if the filter is not matched, okay, so in that case, so what will be the efficiency? So generally we say that for a match filter, okay, so we can say that efficiency is nothing but what, a ratio of what will be the peak signal to noise ratio at the particular match filter value, okay, at the match filter. And that efficiency again depending upon that what will be the shape of this filter. Okay, we can say that a shape of a filter, and that shape of a filter, that will be depending upon the what will be the input signal to. Okay, so we can say that input signal, if we have a rectangular pulse, the shape of the filter is to be a rectangular one, and for this a maximum efficiency, or to get the maximum efficiency, so in that case we need to consider the a optimum bandwidth. Okay, so we have, or we should have the optimum bandwidth, so that we are getting the maximum efficiency of a filter, and that maximum efficiency is depending upon the bandwidth. So different input signal, so different bandwidth. So for a different input signal, they have some particular optimum bandwidth, and that optimum bandwidth will provide you what will be the efficiency of a filter, whether it will be the match filter or a non-match filter. And we have seen that earlier case, that is the match filter, and that match filter with a white noise. If we need to understand that a match filter with a non-white noise is a Gaussian. Okay, so in that case, what will be the a function here? So in the condition for this non-white filter, so we already defined a function, frequency response function, in terms of the gain. This one is about s of f exponential of minus j twice by ft1, and we can define that filter ratio function, frequency response function, that will be maximizes with respect to the given particular ni power. You can say that ni of f. Okay, so this one we can define a signal to noise ratio function. For this condition, when we can say that to maximize the signal to noise ratio, when we have the non-white noise, okay, and in that case we have defined a h of f, that will be for the white noise function, and for this non-white function we can, if just s of whatever the h of f equations we are writing here, so that h of f equation, that can be written in terms of what, 1 by ni of f. We have a here, we have the s of f, ni of f, and that will be the complex conjugate, and exponential of minus j twice by f t1. So this one is a function. Earlier function that is about a white noise. This one is about a non-white noise. And that non-white noise is nothing but what? It has a two filter function. They are in a cascaded form. And the first filter function, it has a frequency response of what? 1 by ni of f, and that act as a noise spectrum, okay, for this a white noise there, or we can say that uniform stationary noise there, or we can say that this particular function is nothing but a whitening filter. And this particular second filter, it act as a match filter there. And that filter will be act as a match filter even if we have the input is a white noise and the signal has a spectrum of S of f by Ni of f. Okay, that's all about, we can say that, a match filter with a white noise and match filter with a non-white. With this, we stop here. So thank you all.